All right, ladies and gentlemen. So for Formative 7.2, we were looking at uh, the hot packs versus cold packs. So the chemical formula we looked at first was iron and oxygen makes iron oxide plus 1648 kilojoules of energy. So the first thing we need to notice is that this is right here, which means it's on our reactant side, which means it's getting released. All right. So that energy is getting released by the end of our reaction. All right. So if we're looking into gives us instructions that you don't open the outer package to expose the package to air. No shaking is necessary. Use the hand warmer in an enclosed area such as with air, such as a pocket or a glove. And it can reach up to 135 degrees Fahrenheit or on average in a maximum of 158 degrees Fahrenheit, and it's going to warm up immediately, but it'll take up to 20 minutes to get all the way to that high point, and it lasts for 7 hours. Okay, so really it's just telling us that it's going to react, it's going to heat up, right? Which means it's releasing heat, right? So the first thing it says, identify the components of the system. So that means our system is that iron, so the 4 moles of iron and the 3 moles of oxygen, right? We don't need to put moles there. We know that's moles. The 3 moles of oxygen are making the iron oxide, the 2 moles of iron oxide, right? And so that is our system. That is what we're looking at, the air and the surroundings that's outside of our system. So that's our system. So now we need to draw a graph that shows the energy transfer for that system. So we need to draw our X and our Y axis. There we go. And we need to label it. So we have energy on the left-hand side on our Y axis, and we have time on our X axis. So we have those two parts to our graph, right? And so that tells us that the energy can change, right? And so now we're looking specifically at how that energy changes. So we have our reactants, and because we know that energy is being released here, we know that the energy at the says it's going to be leaving. That means our reactants should be higher than our products. All right. So on our graph, that means I'm probably going to start somewhere up here, all the way closer to the top instead of starting closer to the bottom because I want my energy to leave. All right. And what I need to put on here is I need to label my reactants. Okay. So it says up in our problem, it says 1 point for labeling products and reactants, which means we need to label our reactants over here. So we have 4 iron plus 3 oxygen. All right. So now our graph. Our graph needs to get to a lower temperature somewhere around like here, right? Because we need to release energy. Energy needs to leave more than it needs to be absorbed. But in order for energy to leave, it first has to get some energy absorbed. It needs to activate, right? And that just means that it needs some energy to break the bonds. So we're going to have a little hump or a little loop that goes up first. In this loop right here, this area is our activation energy. And that's just our energy needed to break the bonds, all right? So in order to break any bonds, we need that energy, right? And then it's going to go down, and then it's going to come out way down here where we're going to make our iron oxide. So we've made our iron oxide our product. So now we've labeled our parts, our pieces, all right? And so then the rest of this section from here to here, this is going to be our delta H. That's our energy that we're releasing. And that's going to be our negative 1648 kilojoules, right? That's the number from the top. And it's a negative now because it's not in the reaction anymore. So it needs to be released. So either we can say negative or we could just say 1648 is released. We also need to identify that this is an exothermic reaction. So energy is released. Right? So energy gets released here, and that's why it's an exothermic reaction. And then last part, it says, use the relationship established to explain the formation of breaking of bonds to predict the total energy change. So for that, I just want you guys to talk about the fact that more energy was made when bonds were formed than when bonds were broken. Right? And that's evident because it took this much energy to break our bonds, just the top half, right? So the top half was our energy that it took to break the bonds. So way up here, this part. And then to form new bonds, it was all of this energy to come down here. So we had an overall change negative because it was more energy released when the new bonds got formed. All right. So that was our first question. And then our second question was looking at this lovely table right here, where we are looking at the enthalpy of formation. And so these values are already negative for us, which works out in our favor when we're looking at our delta H equations, right? So for this one, we're looking at the graph, and the first thing it tells us is that all of this energy was needed to break the bonds way up here, and just a tiny amount of energy was released, which means that in this graph, we have an exothermic reaction, or sorry, not exothermic, endothermic, because more energy was absorbed than there was released, right? It absorbed energy. And that's because it absorbs all of this energy way up here to get to the top to activate our reaction. And then it only released this much energy, so it absorbed a lot more than it was going to release. So now if we take a look, we have a few things to do. We need to identify if the energy being transferred so we can see that energy is being absorbed, not released. And then we need to solve for our delta H, right? So our delta H right here is, again, our products minus our reactants. So we need to find the H of our products. And so if we look for our products are NH4 in an aqueous solution, which means that the two things are going to separate because they're already in water and they've dissolved in water. So we're looking at the ions now. So we're going to look at the NH4 with a positive charge plus the NO3 with a negative charge, okay? And then for H of our reactants, that's just going to be the solid NH4, NO3. So that's just going to be the one thing together. All right. So now we can just take those numbers and plug them in. Since it's an equation is a 1-to-1-to-1, we don't have any coefficients. So that means we can just take our NH4, which is negative 132.8, plus our NO3, which is negative 206.6, and we can add those together to find our product side, which is negative 339.4 kilojoules per mole. And again, when we do those sig figs, we are in the decimal points here and in the decimal points here, which means we need to be in the decimal points right here. Our reactants, so we just have the one, which is negative 365.1 kilojoules per mole, right? So that one isn't changing a whole lot, okay? So now we can take our products, so our delta H, we can take our negative 339.4 minus the negative 365.1. And when we solve that, our delta H becomes positive 25.7 kilojoules per mole. And sig figs again, because we're subtracting, we want to use decimal points. And so they both go into the ones place. So that's why we end in the ones place there. So our delta H is 25.7 kilojoules per mole here. Right? If you have any other questions, let me know, guys. Otherwise, have a good rest of your day.